he moved to IIT Delhi. He was also be a Vice Chancellor of University of Hyderabad. Professor Ramsamy is one of the pioneers who introduced nonlinear dynamics in India and trained several people in this area of research. In fact, people from nonlinear dynamics collaborating with Professor Ramasamy for more than 30 years. So I can say Professor Ramasamy is associated with Bharatdasan University for more than 3 decades. I know many of us have inspired by talking to him. He works on several topics in nonlinear dynamics, including classical and quantum chaos, semi-classical quantization, molecular dynamics, cluster physics, disordered systems, and statistical physics. I have pointed out only a few topics. He works on several topics. He had organized several conferences and served as editor for several journals. If you want to know more about him, please visit his homepage, which he designed very beautifully. With this short introduction, now I invite Professor Ramasamy to deliver his lecture. It is over to you, sir.
Thank you very much, Senthil. And good morning to all the students at Bharathidasan. I had originally planned to be in Trichy today, but I don't know, Omicron, Delta, Tau, God knows what, all these new letters of the alphabet we are going to learn. It's just, it's just bad timing, I guess. Anyway, what I thought I'd do today is to tell you all about some, I didn't quite understand that you all haven't taken a course in nonlinear dynamics yet. Professor Senthil just told me that, 5 minutes ago, and so I cannot rewrite my entire lecture, but I'll go certainly as slowly as possible. But hopefully not slower than necessary. Right. Let me start by just uploading my presentation. Just a second. Just one moment, please. Let me get my... All right. Okay. I hope everything is visible, right?
Yes, sir. Yes.
Okay. So I want to talk about the notion of synchrony in nonlinear dynamical systems. I know that you all haven't studied nonlinearity or too much about nonlinearity yet. You don't know what synchrony is, but that's something that's not too difficult to introduce, and so we can discuss that. What generalized synchrony is a sort of a slightly specialized way of looking at it. We'll do that as well. But I understand that you all have done classical mechanics, so you do know things about dynamical systems. Yeah. At any point during this talk, please just stop and ask a question if you like, or you tell me to rush up. It's all boring, 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 or any comments are welcome. All right. Okay. Now, synchrony is something that's very common in nature, and it's something that we all are we have an instinctive appreciation of it. This is the most common form of temporal correlation that is easily observed. Whenever something is synchronized with something else, you can immediately see it because they are both moving at the same in the same time, in the same place, in the sort of similar place, and so on. Now, as you can see, both these clocks are pendulum clocks, and they are certainly not synchronized because they're just moving randomly with respect to each other. If they were moving with each other, we would be able to recognize it immediately. Now, the person who first pointed out that this was unexpected and unusual was Christian Huygens. You will, we've all heard about him because of his sort of pioneering work in the 1600s. He was, in fact, the first person to build a clock, a reliable clock that would keep the time accurately. But what he observed was that there were two pendulum clocks that he had designed, and they had both been suspended from a common brand support over here. And this is a drawing that he had made, and they were supported like so. And what he noticed was that regardless of how you set them off, unlike these two chaps, because these are not connected with one another, right? And these are just moving around randomly. But Huygens's clocks were connected via this support over here. And what he noticed was that pretty soon after, when this pendulum was at position, whatever this letter is, D, this pendulum was at position K. When this was at position E, this was at position G, and so on. All right? So, and then he observed that this happened, and not only did he observe it, he had a explanation. And he said that, look, this is happening because they are both supported from a common beam over here. And it's because of this coupling that you find that they are both synchronizing. Now, you can do this experiment again at this in this day and age, but instead of having pendulums that are hanging from a common support, people do it with these metronomes. I presume this video is visible, is it? Senthil? Just a question over here. Senthil, is it all visible, or shall I just go to the...
Can you zoom it, sir?
Okay. Okay, I'm just going to go onto YouTube and watch it over here.
No, we are not seeing the pictures. No, we are not able to. We are not able to see. Yeah.
So these are, a set of 5 pendulums. They are.
No, sir. Excuse me, sir. We are not able to see the.
You're not able to see this?
Yeah, we are not able to see the movie.
Okay, just one second. I know what the problem is. Just one second. Let me support. I'm going to support my entire screen. And then, can you see my entire screen?
No, sir.
No.
It may come up, but no.
Okay, wait on this. Oh, damn. Just a second. I should be able to. All right. If need be, let's just stay with.
Okay, sir. Okay.
We'll stay with the smaller screen over here. Y'all can, students can please go and see it later on. I mean, right now. Okay, so let me just introduce what this is about. These are small pendulums. They are, timekeeping devices for musicians. They are called metronomes. And there are 5 of them that are placed on a wooden beam over here. What this student is going to do, or what this person who has made this video, incidentally, it's a very popular thing to do on YouTube. So any YouTube search of synchronization metronomes will give you a few million hits. Okay, if not a few million, a few hundred anyhow. And these are all going to oscillate independently when they are unconnected to one another, or when the connection is not a real, is not a useful one. After a few minutes, what the student does is to put them on a moving, on something that can move, and pretty soon you'll see that the whole system synchronizes. Okay, so you just watch that. All right, so they put them on two Coca-Cola or something similar cans, empty cans, and you can see that the beam is now moving. Just to illustrate again, here you see they are, when you can hear that they are really not synchronized. They're just moving arbitrarily. And the moment you put them on, you can hear the synchronization, right? So this is what all right, so you saw how, even though they all started out independently, because of the coupling, they just got exactly into phase. You can just look at that. And this will stay on for a while. But because these are physical systems, there's a little loss of synchronization over here. And you can again hear that. But you see something interesting over here. Just look at the first and the last one. The first and the last one have a different relationship with regard to the others. And there's some, point of the story is just that, look, there are interesting things that happen when you couple many of these systems together, but you can basically understand this phenomenon just from classical mechanics. Now, I know that all of you have had a course in classical mechanics. Yeah, and just one second. Let me just stop sharing for a moment because this is a there are many of the students that I can see in Vignesh Saravanan's screen over here. So the question that I'm asking, Senthil, through you to everybody is, in classical mechanics, have we done normal mode analysis?
I think Dr. Muruganandam is handling the classes. I think he is about to start. Yeah, small oscillations, he is about to start.
He is about to start small oscillations. And hi, Anand.
Hi, how are you?
I'm good. All right. So have the students been exposed to what are normal modes?
Not yet, actually. At least first year, not yet. Second year might be.
First year, all right. So, well, there are some students who will know what I'm talking about, and some who will not know. So let's just let me get back to my this thing. So, all right. So from basic classical mechanics, right, if I was to just take two identical pendulums and suspend them from a common support over there, but instead of letting that support move, let me just put a spring between them. Then the kinetic energy is just 1/2 of dq1 by d. Q1 is the angle over here, and for the first pendulum, and Q2 is the angle for the second pendulum. So the kinetic energy is 1/2 Q1 dot squared plus Q2 dot squared. Dot means d by dt. You all know that. And the potential energy is, for the first pendulum, it is Q1 squared by 2 for small oscillations. And those of you who haven't done small oscillations so far, Professor Muruganandam will be dealing with it soon. And the potential energy for the second one is Q2 squared by 2. And the coupling between them is alpha times Q1 minus Q2 squared. All right. Now, there's a way of studying these systems in classical mechanics to find out what are the collective motions of these two pendulums. And this is what is usually called normal modes for small oscillations. And these normal modes can be easily found for the system of two pendulums. And these normal modes are what is written on the left-hand side in capital letters. So Q1 and Q2. So Q1 is little q1 plus q2 by root 2, and Q2 is like so. And in terms of these variables, the kinetic energy is a half capital Q1 dot squared plus capital Q2 dot squared. And the potential energy will just come out to be very nicely 1/2 of Q1 plus, what is it? Alpha times Q2 squared or something like Q1 squared plus alpha times Q2 squared. All right. And you can see that this is how these modes will come out. And these modes are these sort of the normal modes of the system. And these normal modes are basically, the collective motion of this entity. So one collective motion is when, you can figure out what these modes are. One of them is when Q1 is equal to 0, and the other is when Q2 is equal to 0. And when Q1 is equal to 0, you notice that little q1 is exactly minus Q2. And when capital Q2 is equal to 0, then you find that little q1 is equal to little q2. Now, little q1 is being equal to little q2 is basically when both the pendulums are moving along together with each other. Capital Q1 equals to 0 is when they are moving in opposition to one another. So when they are moving together in the same direction, it's called synchrony. And when they are moving in the opposite direction, it's called anti-synchrony. Now, a proper and detailed analysis of the Huygens problem is much more complex than what I'm doing over here. This is just two pendulums connected by a spring. The other system that Huygens studied, there is no spring, but you've got some platform that moves about, right? But the physics of synchrony really starts with this idea that when you've got a lot of independent systems, the collective motion can have a certain type of character, and this collective motion is what we are going to try to describe. Now, one of the problems is that we have, described this for a nice harmonic oscillator or this pendulum with small oscillations, but most systems are not linear. And I'm sure that you've already had an introduction to some of these things in the other lectures that people have been giving you. One of the most well-studied nonlinear systems, most systems are not linear, but the commonest studied nonlinear system is just like for linear systems, the most commonly studied one is this pendulum with small oscillations. For nonlinear science, the pendulum with small oscillations is the Lorenz Attractor, or what's called the Lorenz system. This is a set of three equations, three differential equations of first order. And they're sort of all very simple, almost linear. So since it is almost linear, you can see that there are some analysis that you can do quite easily. One of them is that, the one fixed point of this system, what is that fixed point? That fixed point you can see is x equals y is equal to z is equal to 0, right? Because that will make the left-hand side equals to 0. Usually people study it at this parameter 10, 28, and 8 by 3 for these three parameters. But and it turns out that once the parameters have this value, 0, 0, 0 is an unstable fixed point. And and I understand that you all have been introduced to the idea of stable and unstable fixed points already. All right. Now, this system is sort of been studied very, extensively. And one of the most striking things about it is that, if you start at some initial condition, this variable x just oscillates, but it oscillates in a fashion which cannot be predicted. See, for example, it had 2 oscillations for positive x, then it went in and had something like 8 oscillations for negative x, then it had 1 oscillation for positive x, 1 for negative x, then 2 for positive x, or actually not 2, 4 for positive x, then 1 for negative x, and so on. And you can see that there's no pattern over here at all, right? And the lack of a complete pattern is what people will call chaos or aperiodic behavior. Although there are other ways of thinking about chaotic systems or what have you, but this lack of a pattern means that you can't predict anything. And this inability to predict something is what one simple way of thinking about chaos. All right. But there is a better way of thinking about chaos, and that is to start very close by start these equations. This is after all an initial value problem. You've got the left-hand side has got the, velocities in the x, y, and z direction. You start at some initial point and you can compute an orbit for this system, right? When you do that, this is what the x variable looks like, the y and the z. Now, instead of plotting versus time, if you plot versus x, y, and z, start over here, you can go around on this curve, and you're starting with 2 points, one in red and one in blue. For a little while, they are the same, but after a while, they separate from one another, and in fact, you can start distinguishing them. Then, after a short while, the red point reaches here and the blue point reaches here. So a small initial difference over here gives rise to a big final difference, and this is what is called chaos. All right. So, and this is a property called sensitivity to initial condition or chaos, and you can't predict mostly because small differences become very, very large very, very quickly. But at the same time, you start over here and you'll come on to this object. You start over here, you'll come on to the same object. So there is a instability inside this object while having stability or attraction of this thing. All right. Now, why I say this thing rather than because there is no name for an object like this. It's called a strange attractor. It's, it looks kind of flat, but it's not flat. It has some, it has a dimension somewhere between 1 and 2. Or is it between 2 and 3? I think it's between 2 and 3. It has some dimension, all right? It's a complicated object, but these are attractors. So no matter where you start, you will start over here. Also, you will go onto the same object. You start over here, you'll go onto the same object, and you can play around with this as a fascinating system. All right. So when we saw this thing over here, that you've got nice small oscillations over here and they all synchronize, we saw that movie. And like I said, the basic understanding is that you've got normal mode analysis and so on. Now, you can imagine that if small oscillations in regular oscillators, if this could, synchronize easily, because of this unpredictable motion and this oscillation of this chaotic system, it'll be just much, much more difficult. It was a big surprise in 1983 when 2 people in Japan, Fujisaka and Yamada, and later on Pecora and Carroll in the US, they showed that chaotic systems can also be made to synchronize. via something called the master-slave coupling. Just one second. All right. So this master-slave coupling is the following. You've got take two Lorenz systems. You've got x dot, y dot, z dot, and this is what I've just written down on the other screen, right? Here I make a copy of the same system, except I replace over here all the x dots. In these equations, I replace this x prime by just x. Namely, I take the output x from the left-hand system and I feed it into the right-hand system. So this equation just becomes redundant. The first equation on the right-hand side is redundant. It doesn't matter. It doesn't affect anything. Because over here, instead of x prime coming in, which should have been the case, all you have is x coming from the left system. So this is the master. Oops. This is the master, and this is the slave. And the slave has to follow exactly what the master says, because the x over here is the input from the master. Now, when you have something like that, what happens is that if I take the one Lorenz system in purple and the other Lorenz system in green, I'm going to switch on this master-slave coupling at time t equals 10, right? And you notice what's happening. Before that, the two of them are totally uncorrelated. It's like my two pendulums right at the beginning, the two clocks that weren't connected. We said that, they were just oscillating as they like. This green chap is going wherever it wants. The purple chap is going wherever that wants. I switch on this coupling at time t equals 10, and very quickly, the two of them become identical. It's not that I didn't draw the green signal after this point. It is just that the green and the red signal and the purple signal are identical. All right. So the dynamics becomes identical while remaining chaotic. I mean, notice that they are both still oscillating up and down randomly, but they are doing so together. If I calculate a distance between these two, and the distance would be x minus x dash squared plus y minus y dash squared plus z minus z dash squared, if they are identical, then that distance goes to 0. And what you can see over here is that if I calculate the distance, I mean, here the distance is varying randomly, okay? And it's of order, this is not 1, but it's very large, right? It could be, I don't know, 200 or something like that. It's just changing, oscillating as it likes. And then I switch on the coupling, and then the distance between these two just goes rapidly to 0. This is on a logarithmic scale, so you can just see that, boom, it just goes down to 0. And the distance is decreasing exponentially because time is linear here, and the distance is logarithmic, so it is an exponential decrease in time. Right? Okay. Now, this is a topic called chaotic synchronization, and everybody has been studying it with great interest for the last 30, 40 years or so. A lot of people, and I know that in Trichy also, there's been a lot of work in synchronization and different kinds of synchronizations, all sorts of things. If you haven't heard more talks on synchronization before, hold on, because whenever studying nonlinear science, this is a very important part of it. All right? Okay. Now, let me stop for a moment and just check with everybody as to where all of you are.
There is a question in the chat box.
Right. Tell me.
Yeah, there are two questions.
One second. Okay.
Yeah.
So Prashant, you're quite right. Due to the common base, why is there a synchronization in the same phase? Actually, what Huygens saw was not with the same phase, what he saw was with opposite phases. So if you want to think of the two normal modes, what he saw was the Q1 normal mode and not the Q2. All right. Is it possible to, yes, now you just hold on. Just hold on for a few minutes, because my main talk is to say how can we what is synchronization and how do we design it. Okay. Okay, so this is a talk which is not just on synchronization. I want to present you all a way of thinking about synchronization, which is a little different. All right. Okay. So good. I mean, but otherwise everyone is with me, I hope.
Yes.
Those of you who are not sleeping, yes, Sai, go ahead.
Hi, Professor Ram. So just a quick question. Typically, in let's say Pikovsky or the standard textbooks, the notion of synchronization is also presented with kind of perturbation. I know that you can discuss synchronization outside the perturbative regime, but what drew my attention is that in the coupled differential equations that you showed, the target control, the x and y, x prime, y prime, when you replace them with x and y, they can be very large, right? And so in some sense, they would drive the system, and they come with a negative sign. So they drive the system towards basically locking. So is it just generic phase locking, or is it actually genuine synchronization? I mean, in the sense, if you plot an Arnold tongue-like thing, would you see it? I understand this is maybe a question outside the scope of many students here.
But actually, just hold on, Sai. I'm going to discuss this in the context of driving.
Okay, very much.
All right. So maybe some of it, that I do understand, I will try to present it that way. Yeah.
Sure. Thanks.
Okay, I'm just trying to make this. Okay. So let me just get back to. Oh damn! Where is my talk now? Just one second. They should have a some helping tool for the perpetually bewildered. Is the screen visible now?
No, sir.
Okay, all right. Okay, there we are. All right. Now it should be. Yeah?
Yes.
All right. So, there's a whole bunch of different kinds of things that are called synchronization in one way or the other. I'll worry about it when I come in. Okay, so what you saw was one example of something which is perfectly synchronized. There are two or three slightly variations of this that I want to address. The first one is what's called phase synchronization, where you take this system of RUSA oscillators, make two of them, and when you make two of them, you couple them in a sort of a simple way. And what you observe is that the two of them are they're sort of not identical, but they are but their phase differences, because these are systems where you can define a phase in a particular way. What happens is that the amplitudes of oscillation are completely uncorrelated. So if A1 is amplitude of one of these variables and A2 is the amplitude of the other system, all right, those two are uncorrelated, whereas the phases at a certain point, the phase difference phi1 minus phi2, that just becomes completely correlated and they're phase locked. Just to point out what Sai was talking about. I'm going to come back to this in a different context momentarily. So what I want to just draw your attention to is that when you say that something is synchronized, it turns out that the simplest way of looking whether something is synchronized or not is to ask, how do the variables of one system, when you plot it against the other, what does that picture look like? All right. Supposing they're completely uncorrelated, you've got some variable x1 and you've got another variable x2, and these are uncorrelated. If they are uncorrelated, then they go between some ranges, the maximum value of x1, maximum value of x2, and so on. There you see, since they are uncorrelated, things are just going around and around and around. And if you wait for sufficiently long time, you'll just completely color up this box as black. Take the other extreme. If they are completely synchronized, then both of these are identical. So x1 versus x2 will just be going along a line. It won't be going smoothly. It'll be going up and down and up and down and up and down in a non-repeating chaotic fashion, but it'll be on a line over here. Now, if something is phase synchronized, there is a relationship between the two. And this relationship comes about, looking at a nice little picture like that. All right. Okay. So the point that I want to draw your attention to is that if there's completely uncorrelated, this picture is in 2 dimensions. If they are completely identically correlated, there we have it in a straight line, which is 1 dimension. It is a subset of this totally allowed space. And this subset, it's a lower dimensional space. And this is an intermediate case where it's not completely 2 dimensions, it's not completely 1 dimension, it's somewhere there, but it's something which is of lower dimension. Okay, so there again you have complete synchronization and phase synchronization showing up as these 2 kinds of behaviors. Here, the amplitudes are uncorrelated, but the phases are the same. And here, not only are the amplitudes correlated, but the phases are also identical, and you get a curve like this. Now, I'm going to try to generalize this motion, these notions slowly, but let's just ask a question. How do systems synchronize? First of all, we think of them as being either mutually coupled, like the Huygens pendulums, or what I showed you earlier about Pecora and Carroll, that you have a system which is a master and it drives the other system, which is a slave. Right? There is a third way in which we can think about it, and this is when both systems are driven by or which are coupled to a third system. Now, all these are different ways of thinking about how systems can synchronize. I'm not saying anything particularly deep over here. I'm just saying that they have to be coupled. They can be coupled weakly. They can be coupled strongly, or they can be not mutually coupled. So they can be coupled to a third one. Now, this coupled to a third object is something actually that all of us are familiar with, because as we know that the Earth and life on Earth is completely controlled externally by the sun. And the sun is, the sun is not an oscillator. The sun is what it is. But the light on Earth, the amount of light and heat on Earth, that is a periodically varying function, right? Every day the sun rises, and in Trichy, for example, it rises close enough to 6 o'clock. You are very close to the equator, and it sets at roughly 6 o'clock. But you have oscillations that are almost periodic, and people get up and go to sleep at highly correlated times. If you just look at percentages of people who are awake at, let's say, 10 o'clock in the morning, it'll be a very large percentage, mostly because the light makes it impossible to sleep. And likewise, at 10 o'clock or 11 o'clock at night, most people will be asleep because of lack of light and so on. Now, so this is a way in which people can appear to be synchronized, even though they're not interacting with one another that way. We are all interacting with a third body. All right. So there are variations of this kind of thing, but a framework which includes all these is the idea of generalized synchronization. Now, this think that I was just alluding to the fact that we are driven into a state of synchrony by the sun or by an external oscillator leads me to just represent these ideas over here in the context of forced oscillations. Now, I presume that this has been covered in your classical mechanics course. If you take a simple harmonic oscillator, all right, and here is your simple harmonic oscillator, which is Q double dot plus omega squared Q equals 0 would be the equation for a harmonic oscillator with frequency omega, right? No, I'm sorry for this double plus, but anyway, okay. And here I'm putting an external forcing, which is F cosine omega t, right? Now, Senthil and others, I presume that this is something that has been discussed in
yes. Even they have studied it in their undergraduate course.
Yeah, they would have studied it in an undergraduate course. All right, please excuse this double plus in the. It should just have been a single one. All right. Okay, so you know the solutions for this second order differential equation. When omega is not equal to omega naught, when these two are not equal, then you know that the solution is just C1 cosine omega naught t plus C2 sine omega naught t plus F over omega minus omega squared cosine omega t. Right? So the solution for the oscillator is its intrinsic oscillation, which is the omega naught part, plus an aspect of the forced oscillation, right? But we don't want omega to be equal to omega naught, because when omega is equal to omega naught, this term will blow up. And instead, we have to solve the solution, solve this differential equation in a different way, and we get C1 cosine omega naught t plus C2 sine omega naught t plus F over 2 omega naught times t sine omega naught t. Right? Now, I know this is old and boring, but supposing in this particular situation, omega was equal to 3. When omega is equal to 3 and omega is equal to 3, when omega naught is equal to 3 and omega is equal to 3.5, this is the kind of solutions that you get. So you see that there's one basic solution that you get at 3. Then you get another solution which comes from this term. Now you've got a sum of two cosines, so you will have sums and differences that are coming out because of this, and that gives you this bigger envelope over here. All right. When you get to omega is equal to 3.3, the sums and differences change, and you get another envelope over here. Point that I want to make is that whenever you have a forced oscillator, you have the so-called Beats phenomenon, okay, that you can see in the last of the pictures over here. And this Beats phenomenon represents the fact that the system responds in two ways, one at its intrinsic oscillation frequency and one at its externally driven frequency, right? Okay, so this is what I'm just said. The frequency of the external drive and the basic oscillation frequency and the interaction of these two, which are just basically trigonometric identities, sine plus sine gives you sine of the, difference, or cosine of the difference, and so on, okay? Now, I just want to, point to the fact that if I say if I can rewrite this equation in the following way, I can rewrite Q double dot plus omega squared Q is equal to Y, where Y is the solution of this differential equation, namely Y double dot plus omega squared Y is equal to 0. All right. Now, all of you have studied this differential equation. You can solve it, and immediately you know that the solution is C1 sine omega t plus C2 cosine omega t. So I choose some initial condition for that, and you know that I can immediately get a solution which is just f cosine omega t for the second equation. So what I've just done is to rewrite these two equations, but in doing so, I want to point to a nice structure that this problem has. This is basically two coupled oscillators, except that this oscillator 2, which is written in the variable y, is unaffected by oscillator 1, which is written by the variable q, whereas oscillator 1 has got oscillator 2's variable coming in. So if I want to just think about this as an autonomous system that is without any time dependence in the, over here, no cosine omega t, I can think of it as two coupled second order differential equations with what is called a skew product structure. Namely, this doesn't affect, q doesn't affect y, but y affects q. All right. Okay, so when dealing with a forced nonlinear oscillator, these basic features get altered in some way. The solutions, and Sai, this is a partial attempt to answer some of your, the points that you were raising. The solutions now have additional terms which are like extended Fourier components, all right? Because I can, if I now want to make this system nonlinear, I'll be adding terms which are q squared, q cubed, and so on. And those can be done in a, you can think about it as Fourier components. In some cases, these can be solved perturbatively, but in general, they cannot. All right? And this is why one would think of this as genuine synchronization rather than phase locking, is that the solutions are modified, but they carry this characteristic of having intrinsic oscillations plus forcing oscillations plus beats, namely superposition. So this is what I'm just offering is a different way of looking at how two systems interact with one another. All right. So let me just stop again for a moment, and
I'm not seeing any questions.
No, I know there are no questions, Senthil, because I'm losing somebody, but have I lost Sai is the question.
No, I'm here.
No. What I mean is that, so I'm just presenting a different, okay, so one way of thinking of synchrony is normal modes. A second way I'm now suggesting is forced oscillations.
I see. Yeah, I have to, well, I mean, maybe we can talk offline about this because sure. I want to discuss the difference between centers and synchronization because, that subtle difference is the thing that always bothers me that I don't fully understand. Because normal modes, you can always also discuss that in the context of centers.
All right. So anyway, so this is the, okay, so no, I mean, I hope are the students with me on this one?
Yes.
Yeah.
I mean, I will
generally okay, right?
Yeah.
Okay, great.
You can continue, but I will talk to them to raise some
questions.
Yeah,
sure. All right. So, all right. So, what is generalized synchrony? All right. Generalized synchrony is basically asking the same question. When supposing you have a, you see, we saw this particular structure over here. This was a linear oscillator forced by another linear oscillator. All right? And when we saw that one oscillator was being forced by the other, what we saw was that the solution had some component of the intrinsic solution and it had a component of the forced solution. Now I'm just going to say, supposing I have the same structure, except that this is now a nonlinear oscillator, and this is also a nonlinear oscillator, and the output, this y is the output of a nonlinear oscillator, with which is now driving this one. All right. So when you have this particular kind of a structure, keeping the skew product nature of the system in place, it becomes possible to talk about this idea of generalized synchronization. All right. So generalized synchronization is the following notion. Supposing you have two systems, x dot given by its own equations, y dot given by its own equations. This can be one dimension, any number of dimensions for x, any number of dimensions for y. They can be completely different systems. Now we couple them. And we couple them with some functions, zeta x and zeta y. And we will say that they are in generalized synchrony if the following happens. For some particular coupling strength or coupling form or what have you, if the variables of the two systems have a functional dependence, namely if y is given as a clear function of x, then we will say that these are in generalized synchronization. And at this stage, it may be a little too much, but at some point in time, what one can see is that almost every kind of synchronization can be written in this form. All right. Okay. So when you say that two systems are synchronized in some way, whether they are in phase or anti-phase or what have you, what we are basically saying, there's a map between these two systems that relates the variables of one system with the variables of the other. This map could be that, if these two systems are coupled, x is equal to y, then the map is the identity, right? But the point is that as I showed in the earlier picture, when things are in some kind of synchrony, the motion, when it appears on a lower dimensional part of the phase space. So this kind of way that, that the motion just gets constrained to lie on a lower part of the phase space, is synchronization, and that lower part of phase space is what's called the synchronization manifold. All right. So what I've looked at is the so-called master-slave kind of coupling, but when you've got an external drive, and you have something which is coupled, the external drive could be now completely chaotic because I've allowed the external drive to be a nonlinear oscillator. All right. Now that is driving some other system and you're getting some response, and this also looks like some crazy signal. All right. How do we know that they are highly correlated? So one way of figuring out whether they are highly correlated is this example I gave you about all of us waking up at more or less 6 o'clock in the morning and going to sleep more or less at 10 o'clock at night, right? Because we are both being controlled by the external drive, which is in our case, the sunlight. So you make the external drive one response unit, and you make a copy of this response unit, identical copy. This is going to be acting independently. But if they are responding exactly to the drive, then it has it has this particular response. And the second system, because it's the same drive, will give rise to the same kind of response. So now you look at these two signals and say, aha, they are both identical, and therefore this must be completely driven by this drive over here. It must be in generalized synchrony with the drive. So this is a way of determining whether something is completely determined. All right. So it's a small exercise that you all can do, and I'm going to suggest that you all work. You study these chaotic systems, and this chaotic system over here is what's called. It's a map. It says that x, new value of x plus 1 is just f of x, and x lies between 0 and 1. and f of x is just 4 times the square root of x into 1 minus the square root of x. It's just a simple function that anyone can play with. All right. So here is the dynamics of x. X just depends on f, and it only depends on x. Y, on the other hand, depends on the same function of y, but it also depends on some amount of x. So this is an example of the skew product structure that I was telling you. The dynamics of y depends on x, but the dynamics of x doesn't depend on y. Now, let's just consider these two systems. As I keep changing the value of epsilon, what happens is that this is for epsilon equals 0. The two of them are just completely uncorrelated. You know, x and y are just varying as they like. As I increase the value of epsilon, I reach a particular stage where y versus x, it's not a nice function or anything like that, but it's something that depends, and you can see it is different from the uncorrelated part. All right. And if I increase further the value of epsilon, at some point, x and y become identical and they just fall on this straight line. They are oscillating wildly on this straight line, but they are, you know, x versus y is the same straight line. Now, if I take another copy of this system, namely if I try to do something like this, I'm making a second copy of this system, what I'm calling response 2, and I call this y prime. All right, so y prime of I plus 1 is f of y prime. And now I make exactly the same connection with x over here. So the drive, if you like, is the same, and the responses are the two different ones. When epsilon is 0, the two of them are uncorrelated, so everything is just moving around completely. This is y versus y prime. Here, notice that x and y have this complicated relationship, but y and y prime are the same. That is to say that at this point, y and x are in generalized synchronization. And here, y and y prime are all on the same straight line. So here now, you notice that y and y prime are identical over here, even though y and x have got a rather complicated situation. So this is what generalized synchronization is. Even though the behavior of x and y may not look like it is identical or any kind of very simple form, by looking at two copies of this response system, we know that the response y has a unique dependence on x, which is why even y prime is the same unique dependence on x, and therefore y prime and y are identical to one another. All right. Okay. So I hope that this is clear. If not, please to ask questions. When appropriate. All right. So this unique function of the drive tells us that that you are in generalized synchrony. And I just want to point out that this is a form of constrained dynamics because you've come to a lower dimensional space. And from classical mechanics, you all should know that each time you add a constraint, you reduce the amount of phase space that you can explore because the constraint has to be satisfied. Now, it turns out that this external drive can be stochastic. By stochastic, it just means that it's noisy. If y and y prime are very similar systems, if they are subject to the same external noise, they become functions of this noise. They have these unique functions of noise, and thus they will behave identically. All right. So two systems that are nonlinear and chaotic will not follow the same dynamics, but if they have the same identical noise, then they become synchronized. And there's been a lot of work done on that. I know that Professor Muruganandam has done work. A lot of people in Trichy have done it. So this is something that one can look at. Senthil has, and so has Senthil Kumar and others. In biology, this is a well-known phenomenon. I've already told you about how we are all tuned to the sunlight, and therefore there's a kind of synchronization. But it turns out that there is a well-known effect, well-known enough to be named after a man called Moran. Mr. Moran discovered that biological populations correlate with the environment. So the environment is like an external drive, and when the external drive acts on sheep populations or squirrel populations in unrelated communities, they turn out to have, this is an example of squirrels in various patches. They're all subject to the same kind of weather, and this is in Finland, all right? So given the weather, what they show is that, in this particular district, the squirrel population fluctuates like so. In a neighboring district, again, the squirrel population is a very similar kind of fluctuation. In a third, it will be something like so. So you can almost tell the weather patterns by looking at how the squirrel populations have varied. So these three populations are so closely tied to one another that one believes that the weathers in this region must be the same because this is your common external drive. All right. So there is a way of thinking about, and so is this one. All right. So these four are all the similar weather patterns. These others have got different patterns and so on. All right. So the common external drive tells you how certain things synchronize. And synchrony over here is, of course, it's a statistical problem. I mean, it's not exact. It is obviously something that will vary. All right. So the idea about this generalized synchronization is the following. And I am going to just say that, because it's actually a sort of a fairly detailed topic, which I would have covered in longer lectures. But Senthil, I should go on for about another 15, 20 minutes?
Yeah, no problem, sir. No problem. Yeah, but there are some questions in the chat box. Do you want to answer now?
Yeah. I mean, it's always good to stop talking and explain oneself. So go ahead, man. Who's asking the questions?
No, in the chat box.
Yeah, I'm looking at the chat box. Prashant Singh and Sanjay. What will result by synchronizing? Sanjay says, what will result by synchronizing two or more dynamical systems? What happens when you have more than two, you have a collective motion. In the most interesting cases, you can have phase transitions. So when you take large numbers of dynamical systems, and we're going to see a few examples later on, you will find that such systems show essentially phase transition-like behavior because you can go from synchronizing small numbers to actually macroscopic synchronization. All right, and this is something which is studied quite often in the Kuramoto model. All right. Okay, is there any other methods to synchronize nonlinear systems? Generalized will cover almost everything, Sanjay. So let's leave that for the moment, and we'll see. I'll show you some initial ideas about how to think about this in a more general fashion. Prashant says, does it mean that converting a linear system to nonlinear system by nonlinear driving force? That is also one way of converting a linear system into a nonlinear system. You have a nonlinear drive. Take a harmonic oscillator and drive it by the Lorenz system. You will have a nonlinear, you'll have a linear response, but the nonlinear drive will give you aspects of nonlinearity in the final response of the system. All right. Yeah, essentially right. Yes, Prashant, you can think of it always in the following way, that if you've got a drive and if you've got a response, the final, if you've got the response which is being driven by a system, what you will finally see resulting is some oscillation that are intrinsic of the response, and then some oscillation that come because of the drive, And the result will be not a superposition of the two, but will be a result of the two. Okay. Shana says when we talk about sync, it's often between the same kind of system. Can we bring about? Yes, we've got to just change our idea of what we think about synchronization. All right. So in order to get to answer Shana's question, let me now get back to the lecture because really, Shanaz, this is about you've got the point of what I want to talk about. All right. Okay. So in this particular system, I've just written this symbolically that x dot is f of x, y dot is f of y. These two can be completely different systems. X can represent, let's say, the Lorenz system, y can represent the RUSA system, or it can be a harmonic oscillator, or it could be a nonlinear oscillator, it could be any old thing. It doesn't matter. We can see this kind of correlation very easily when they are identical, which is why typically, and even I will give many examples of the same, but nothing in the formalism asks you to have the same system. All right. But Shanaz, what I'm going to discuss is the following. Supposing I want this relationship, okay? I haven't specified what is phi, but let's say I want a particular kind of relationship between the variables of these two systems. I want to ask the following question. Can I make them coupled in a certain way so that I can get this particular relationship? All right? And I'll give you examples of what I mean by that. Now, there's a paper that I wrote a few years ago, which basically tries to answer the question in the following way. All right? Any relationship between the two variables defines a lower dimensional submanifold in phase space. All right? When they are identical, it was along that line, which was, the diagonal line. When they were in a phase relationship with one another, it was this rather complicated donut-looking object that you saw on the square, right? So in all instances, anything which constrains or what brings the motion into a lower dimensional space, I can call it a synchronization of some kind, even though it may not be something which is easy to see. So what we've been doing over the last few years is to look at spaces which are of lower dimension, but also have a nice geometric structure. These are differentiable manifolds. It doesn't matter if you don't know what manifolds are. Just think of it as a lower dimensional space where the derivative occurs, the derivative exists at all points. Because the derivative exists everywhere, if I want something to stay on that surface, then what I would like to do is to force the motion to just lie on that surface and have no components which are normal to the surface. So because it's a differentiable function, I can always define a normal at every point. Now, if I demand that the motion has to always be orthogonal to the normal, then I am going to be stuck on that surface. All right. Now, there's a little algebra which is not going to be very interesting, except to say that, look, you've got your system and you've got the coupling, and here is a whole, you've got on the surface that you are interested in, you've got all the normals. You want the dot product of the normals and the motion to be equal to 0. And this equation, when you solve it, it basically says that the coupling term times the vector of normals has to be equal to minus the vector of normals times I'm sorry, this is a mistake over here. It should be an F. Okay, so it is minus the flow, the dot product with the normal. So this is exactly how you will do it. And this set of equations is underdetermined, so you get many solutions. And out of these solutions, you can determine what is the coupling that is required. Right? There's some small, mathematical points which are unimportant over here, but all the details are available in a paper, and which is actually now already 3 years old. And so let me show you what we mean. All right. I've already shown you this example of two Lorenz oscillators that were coupled to each other by this method of Pecora and Carroll, right? And we coupled them, and what we found was that they were identically synchronized, right? Now, identically synchronized basically says that in the phase space there is a diagonal line. Question is, can I make them synchronize on any line, any arbitrary line, not the diagonal? So what you saw was the case where A is equal to 1, B is equal to 1, and C was equal to 1. So x1 was y1, x2 was y2, and x3 is y3. Instead of that, can I make them synchronize for A, B, and C, arbitrary A, B, and C, using the kind of formalism that I've mentioned over here, right? So this is not a curved surface. Now it's another flat surface, but it is an angled flat surface. Now it turns out that if you go ahead and solve those equations, you get these two forms of, you get a value that zeta 1 coupling is this, zeta 2 coupling is this, where you can see the variables A, B, and C occur all over the place. And when you go ahead and you solve your equations on a computer, lo and behold, you get this beautiful scaling. This is your original system, x1, x2, x3. And this one is your Y system, your drive, then it's not drive and response. They are both coupled to one another, but the two variables are in this kind of relationship with one another. All right, that the Y values are always A times the X value. Sorry, the X values are A times the Y values, etc., B and C. All right. The Shanaz, as I said, we've taken similar systems, but here I've taken very different R1 and R2. All right, they're two Lorenz oscillators, but very different ones. And yes, you can make them, couple them so that they behave in exactly the same way, except that the variables of one system and the variables of the other system are related by the scale factors A, B, and C. All right. So this is a way of enlarging your idea of what does it mean to synchronize. By synchronizing, we will say that two systems are synchronized if the variables of one have a unique dependence on the variables of the other. Okay? This unique can mean identical, it can mean something else, but so long as it is unique and specified, we'll say that we can synchronize these two systems. Here's another example. I want to take two Lorenz systems, but I want to make x1 of one system equal to y2 of the other, and y1 of one system equal x2 of the other. And here is, you follow the same methodology and you get this answer, and here's the result. So you find when you couple the two systems, the x variable of one is behaving like the y variable of the other, and the y variable of one is behaving like the two things are just exchanged. All right. And this manifold doesn't have to be a straight line or whatever. It can be a curved manifold. In particular, it can be a quadratic manifold. All right. And I just want to show you that when you couple them in a particular way, all right, you can again solve those equations and so on. You see the manifold, you can see the curvature of the manifold. All right. Of course, this is a 6-dimensional space, so you can't plot everything, but I'm just saying that when you see the solution now is lying on this curved manifold, which corresponds to x3 squared is equal to y3. That gives you that particular curvature, right? Of course, you can solve this in many different ways because this, as I said, the solution is not a unique solution. And you can make, you can make y3 equals the square root of x3. That will still give you that x3 is y3 squared. And that gives you the solution, which is blue. And you can make both of them coupled in, bidirectionally, and that gives you the red. But in all these three cases, as you can see, the solutions all lie on the same manifold. The relationship is the same. The coupling is very, very different. So this is in response to one of the questions which, somebody has already asked. Many different couplings will give you the same kind of relationship between the variables. And what I'm showing you over here is that you can almost design whatever kind of coupling you want to use. And because this is Bharatidasan University and, got friends and colleagues over there, you can see that, you can make a circuit. You can do these different types of couplings, and there you can, here is one case of this scaling by a factor of A, B, and C. All right, so you can actually do the experiment there. This exchange synchrony, if you take two Lorenzes and this is the coupling that will switch around those two, you can see this. Okay, this is not a great experiment because the oscilloscope, so to speak, was also simulated, but nevertheless, it's there. And this quadratic case, you can have one master and one slave, or you can have the first and the second, which are this is the master and that is the slave, or you can have the two of them which are mutually coupled to each other. And all cases you will get the same. You get the same kind of functional synchronization that you can talk about. Now, why is all this important? One of the areas where generalized synchronization has the most applicability is biology. And a number of biological processes are oscillatory, but with very different time scales. You can go from neural rhythms, which are, in fractions of seconds, to ecological and epidemiological rhythms, which are on the order of years or even sometimes centuries, like our SARS-CoV-2 is showing. The last time we had a worldwide pandemic like this was 100 years ago, and now we've got one. You've got annual rhythms, you've got daily rhythms, you've got all sorts of different biological clocks. And one can argue that circadian rhythms, synchronizes everything to the sun. That's why this 24-hour cycle on so many things is fairly common. All right. Now, these, but given the fact that there are so many time scales, and biochemical oscillations are connected to calcium oscillations, but biochemical oscillations could go in the order of minutes. And calcium oscillations are of a different, slightly different type. Cardiac rhythms are on the order of a second for most of us. So you've got all these interacting oscillators of different time scales. And because they're all connected in some way, I'm making the sort of a general assumption, or rather it's just a sort of a statement, that many biological processes rely on some kind of this kind of generalized synchronization for their effective function, right? And there are things that you can see which are, if this an idea of this generalized synchrony. The one common example of synchronization that's given is these Malaysian Fireflies, which I presume you can see on your screen right now. You can see them all flashing initially randomly, but increasingly as time goes on, they start flashing together, right? And this is an example of a large number of systems somehow getting synchronized. Now, what is this synchronization? There is a biological oscillator that is light emitting, but it is coupled to the environment, because each of these fireflies can sense the others in the vicinity, right? Something that I'm a little more interested in these days is this collective behavior of things like, schools of fishes. So here's a large number of fish that are moving around, and you can see that their motion is highly correlated. If you think of each fish as a point in in the ocean, and if there are n such fishes, the total dimension of this space is 3 to the power n, right? And yet you can see all of them are moving together in a way in which it is, there's this spectacular images of these birds that are these starlings, the flocks of starlings which move together. There can be up to 1 million birds in, or 100,000 or more birds together. And you can see that they are all actually, the motion is highly correlated. And it's worthwhile asking whether this is some kind of synchrony or what have you. So one way of thinking about this, in the last few minutes over here, here's an image of these birds, individual birds, not of the same video, but in a similar video. And you can see that the birds are actually moving in, there's a pattern to it. So just 1 second, because I need my, I just need my cursor over here. So I can ask whether, if I take one oscillator and give it the variables x1, y1, and I give the other oscillator the variables x2, y2, how do I couple them so that the difference x1 minus x2 and y1 minus y2 is some numbers, all right? So this is just taking the same idea of the manifold and asking, can I somehow now put in a, if I just pretend that this is the difference in x and this is the difference in y, can I make that happen? The answer is yes, you can. And when you do, you find that you have one van der Pol oscillator here, another van der Pol oscillator over here. And this is the coupling term that will make these two happen. When you do that, you find that these two are spatially separated from one another. You don't have to be stuck with van der Pols. You can do it with Rosler oscillators. The blue and the green are identical Rosler oscillators. They're just separated by a distance in space. All right? But birds or fish don't follow, any oscillator equations. So I just drew a set of, just some arbitrary curve. And I asked, can we make a group of birds or group of points move along this direction with some separation? So there you see on the right-hand side, I've got a group of 20 or so things that are moving around in, along an arbitrary motion like so. And you can see them that they're all highly correlated. I mean, these are not exactly the starlings that I showed you, but you can see now that regardless of what the motion is, some arbitrary thing not following any particular equation, you can make large groups of these actually follow the same dynamics. So I've been having fun in the last few years trying to make drones behave in the same way. So here is a group of 3 drones, and you can't always see it because the angle is right. But this is the master, and these are the slaves, and these have a fixed relationship to one another as they move around. And there's also one other entity which is not controlled by this master. It's a plane that is moving around separately. This is not affecting these two, but all these have got a fixed relationship to one another, pretty much like these the systems that you see over here. And the motion is just some arbitrary motion that, person on the ground was just making them move in a certain way. All right? Okay. So let me just sort of wind up over here. because many of these concepts are things for the future for many of you. What I want to point out is that because synchronization takes place on a lower dimensional submanifold of the space, one way in which to think about synchronization is that it is a constraint. What is it a constraint? It basically says that two variables have got to become identical, or they have to have a certain relationship to one another. So you can rephrase all that as a constraint by saying that something cannot change. So when two variables are equal to one another, then the difference between them cannot change. And the coupling that we are using is like a force of constraint, which you all have seen in classical mechanics. All right. But this is an analogy because the examples that we are looking at are not really Hamiltonian systems. So you can't talk in terms of constraints and etc. And you can't talk in terms of forces. So these are all analogies, and I just want to point that out. What is important in this way of thinking about synchronization is that you are designing you're designing the coupling that you want. And by saying that you want a certain kind of coupling, we notice, a certain kind of constraint, we notice that the solutions are not unique. And you can get many different kinds of solutions for the same result, as you saw in the case of the quadratic, constraining it to the quadratic submanifold. All right. Now, so long as this, this constraint is a differentiable one, it turns out that you can design a lot of things. It allows you to control, but trying to make a very constrained manifold you may be forced to stay on that rather than have the behavior of your original system. So there are pluses and minuses to that. And as I've shown you also, you can put all this on electronic circuits and make stuff. And we are in the process of doing that. And the student who's doing that is Vishal Juneja. The one who came up with this entire scheme is Shahrukh Chishti, and Amrita Punavajala has also been participating in all this. The drones are done by Bot Lab in IIT Delhi, and Soumitra Banerjee and students did the original, the initial electronic circuits. And with that, let me thank you for your attention and stop sharing the screen.
Yes. There are a couple of questions in the chat box.
All right. When we talk about, all right, so in nonlinear biology, humans' emotions can interact. Let's not get into emotions, Prashant, because I get very angry when we talk about emotions. Joke. All right. No. I'm not sure that I know how to answer your question in a serious way because I don't know what this emotional field is. I think there's a lot of interesting problems without having to go nearly as far as that. Okay, I mean, depending on what one is actually dealing with, synchronization between two kinds of systems can be as simple as, us synchronizing with the sun. Of course, we're not identically, all of us are not identically synchronizing. All I mean is that our activity levels, if it goes up during the day, there is something that is getting synchronized. And this is true for almost all living creatures, all right? So let's just leave this emotional question out of it. And Divya Bharati says, what are the possible problems in the lack of synchronization? See, Divya, it's there in the talk somewhere, and it's the following. You see, I've said that there is a submanifold, and you want to bring the motion onto the submanifold. Now, what has also got to be done is to make sure that once you are on the submanifold, you stay on the submanifold. That means that these couplings must make the motion always come back to the submanifold. If for some reason the coupling brings you to the submanifold, but this is repelling, then you have to add additional stabilizing terms. So what you find is that in some cases, it's just not possible to stabilize this submanifold. And then, every time you can come there, you'll be briefly over there, and then pretty soon you just fly away because, these coupling terms are just pushing you away from that surface. Okay. So, in a sense, the lack of synchronization really arises from a lack of stability of this constraining submanifold.
So, any other question from student side? Students? Professor Sai, do you have some questions?
Hi, yeah, if there are no more questions, I'm happy to just ask one more. So, Professor Ram, just again the same thing that, so the manifold constraint, basically, it enforces a coupling, right?
Yeah.
So
it enforces a class of couplings. It doesn't enforce a single one.
Yeah. Now, you could just correct me if my understanding is wrong, but when I was reading about synchronization initially, my impression was that you should stay away from kind of, the analogy, I think in Pikovsky, is the wooden board that's nailed between two pendula. That kind of a thing is too rigid, and of course you expect quote-unquote synchrony of the dynamics, but there's nothing interesting there perhaps to discuss. So how do you discuss, or is it meaningful to discuss the strength of the feedback that that is caused by the constraint that you're putting in?
See, that coupling term, there are some aspects of our methodology that are not very clear even to me. With the strength of the coupling term, frequently it doesn't matter almost. Once you've got the right kind of algebraic term, it turns out that you're more or less, you're coming onto the manifold, and that the strength of the coupling almost doesn't matter. Okay. So yeah, this is perhaps worthy of a longer discussion at some other point in time. So we can take it up then. But I'd appreciate it if you actually read that paper that I have given the citation. It's a FISRA-B.
FISRA-B 2018. Yeah, I noted it down.
You can see the way in which we look at it. Yeah.
Thank you.
Yeah.
Professor Ramsamy, Professor Sai?
I don't, but I do now.
He is from IIT Bombay.
Amitabh is a good friend, so.
Oh, okay. All right. Okay.
Very nice to meet you again.
Yeah.
He has also agreed to give a talk.
Okay, very nice.
Yeah, in February.
Lasha, Shanaz, I just showed you that you can think about spatial synchronization also, or spatio-temporal synchronization, by thinking of birds that are flocking, or but there you see the constraint is actually slightly, it is a very interesting constraint because it could be a time-dependent constraint. Right? That, let's just say that you think of two things that are, that are, the distance between them is varying in time. And, unfortunately, I can only work with simple time dependencies like oscillation or what have you. You can think in terms of spatial, or better still, spatio-temporal synchronization. Yeah.
I think Muruganandam has a question.
Yeah.
No, not audible. Muruganandam, not audible. Mute. You have to unmute.
Or speak louder.
No, I will go to his room and tell him. Next room.
There was another question. Mail again.
Hello, sir.
Yeah, go ahead.
Yeah.
In your slide, non-linear scaling S3 square equal to Y3.
Yeah.
in that plot, you are taking logarithmic to the third variable x3. What is the purpose of that, sir?
Log. I mean, I didn't understand. Just say it again.
Sir, in that 3D plot, x1, x3, in that plot,
what I took the log was just so that, because otherwise it becomes very big. So you just take the log means it just on the scale. That third variable of Lorenz is always positive, so you can take logs if you like.
Oh, okay, sir. Okay, sir.
Yeah, that was just for convenience. If I don't do it, then the scale looks very large, and you can't see that one variable is the square of the other. Okay.
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 Anand,
Am I audible now?
Now you are audible.
Okay. So just this is regarding some clarification regarding the strength of coupling actually.
Yeah.
There should be some weak matter. There should be this weak should be there, no?
No, okay. Like I said, Anand, these are not completely clear to me.
Yeah, that's what I was
We
saying.
need to sort of think a little more about some of these things. So wait for the next papers.
Yeah.
Yeah.
Okay. Good. Thank you. Thank you very much.
So, any other question from student side? So if not, I think it's time to thank Professor Ramsamy. Thank you, Professor,
Okay.
for accepting our invitation and delivering a lecture. So
I'm very happy to do that, Senthil. And if there's anything that the students want to ask, you can please share my email address with them, and I'll be very happy to talk to anyone.
Sure. I will inform your address and homepage, so they will write to you. Yeah, I think I'm able to invite you in person here.
I don't know. I mean, I think you started this whole Omicron business so that the travel would become very difficult.
Yes.
I don't know.
At least we'll check.
Okay. Thank you very much. Sir. Thank you very much.
Thank you. So,
Professor Sai?
Yeah, thank you very much.
Yeah, thank you for participating in the meeting.
No, it was a great talk.
I will reply to you in the afternoon. Okay, sir.
Sure, no worries.
Morning I was busy with some meetings.
No worries, absolutely.
Thank you.
Okay, bye-bye.